This is a lecture on section 2.1, the atomic theory. This will give us a brief introduction into the idea of atoms. Atoms as an idea has been around a long time. In fact, over 2,500 years ago, the ancient Greeks proposed that the idea that all the matter that we see around us, whether that be air or wood or even humans, are made up of very, very small particles that are indivisible, meaning that you can't cut them in half, break them into smaller particles, and those particles were called atomos, or atoms. Fast forward all the way to the early 1800s, the debate was still existent in sciences whether matter was divisible, infinitely divisible. So imagine like you're cutting a slice of butter off. You can imagine cutting a smaller and smaller and smaller slice of butter. The question is, do you ever reach a limit where you can't cut a piece off that's any smaller? And if you reach a limit, we would call that limit atoms. So John Dalton, who was an English teacher, proposed what we would now consider a modern description of matter. And there are 3 points that we'll focus on right now. The first is that an element, whether that be something like sodium or oxygen or uranium or gold, an element is a piece of matter with identical atoms, identical particles that have the same mass, the same size, and the same chemical properties. Compounds are combinations of atoms from 2 or more atoms of different elements. So for example, you might combine an atom of sodium with an atom of oxygen. They always have the same composition. So if I have a compound, for example, carbon dioxide, that compound would always have the ratio of 1 carbon for every 2 oxygens. If there was a different ratio, it would be a different compound. A chemical reaction is the case where atoms are rearranged, but atoms are never created, nor are they destroyed in a chemical reaction. So we've all probably heard of atom smashers, which are these high-energy particle physics devices that can be constructed that can break up atoms into smaller particles. Those do exist, but at this point, a chemical reaction is not nearly as highly energetic as an atom smasher. So in a chemical reaction, we can't destroy or create atoms. Now, let's take a look at an example of a reaction. This one right here is the case where methane, CH4, so it has 1 carbon atom at the center surrounded by 4 hydrogen atoms. So the carbon atom is the dark sphere in the middle, and the hydrogen atoms are the lighter particles on the right. Ratio is 4:1. There are 4 hydrogens for every 1 carbon. We would suggest that these are atoms of carbon and hydrogen. Methane reacts with oxygen in a ratio of 1:2, meaning 1 methane molecule reacts with 2 oxygen molecules. And notice that oxygen molecules are diatomic. There are 2 oxygen atoms in 1 molecule of oxygen. That they react to form carbon dioxide. So carbon here at the center, oxygen atoms around it on the outside in a ratio of 1 carbon and 2 oxygens, plus 2 water molecules, H2O. So 2 hydrogens, 1 oxygen, 2 hydrogens, 1 oxygen. The names are methane, oxygen, carbon dioxide, and water. This is what's called a balanced chemical equation. We'll look at that more in chapter 3. CH4 represents methane, O2 represents oxygen, CO2 represents carbon dioxide, H2O represents water, and the numbers 2 represent how many molecules of each of those compounds or elements are present in the reaction. Now, some details about the history of determining that matter is comprised of atoms. In 1799, Joseph Proust proposed what's called now the law of definite proportions. A specific compound, for example, carbon dioxide, always have the same elements, always has carbon, always has oxygen, with the same mass ratio. Mass is something we can measure. So here are several experiments that we could take in order to measure this. Let's say we have a way of collecting carbon dioxide, and we've collected 123 grams of carbon dioxide, so we can weigh that out. If we were somehow able to analyze the carbon dioxide, we would find that the mass of the oxygen in that carbon dioxide would be 89.4 grams. Furthermore, we would find that the mass of carbon is 33.6 grams. Note that those two masses add up to 123. If we take a ratio of 89.4 to 33.6, we would find that the ratio comes out to 2.66 to 1, meaning that for every 2.66 grams of oxygen, there is 1 gram of carbon. Let's do a different experiment with a different amount of carbon dioxide. In this case, we have 50.5 grams of carbon dioxide. We would find that the mass of oxygen is 36.7 grams. The mass of carbon is 13.8 grams. Again, note those two masses added together will give you 50.5 grams. And again, the ratio would be the same, 2.66 grams of oxygen for every 1 gram of carbon. You can get that number just by taking 36.7 and dividing it by 13.8. 36.7 divided by 13.8 would be 2.66. So again, the second experiment gives us the same result. The ratio is 2.66 to 1, the same mass ratio. Again, a third time, 88.6 grams of carbon dioxide. This would give us 64.4 grams of oxygen and 24.2 grams of carbon. That ratio of 64.4 to 24.2, again, would be 2.66 to 1. So that is evidence in support of this law of definite proportions, the idea that a compound always has the same elements. So carbon dioxide has carbon and oxygen, always, and it always has the same mass ratio, 2.66 to 1. That's evidence that there's something about the structure of a compound that is due to the fact that there are indivisible particles called atoms. Now let's take a look at this fourth one here. Notice I didn't write down the mass of oxygen or the mass of carbon, but we know the ratio should be 2.66 to 1. And let's ask, can we figure out in 105 grams of carbon dioxide what the masses of each of these elements would be? So I'll work you through this example. If we have 105 grams of carbon dioxide, that should be equal to the mass of carbon plus the mass of oxygen. Those should be equal to each other. Now, let's ask a question. We know the ratio of oxygen to carbon is 2.66 to 1. So what I'm going to do is I'm going to write this 105 grams as equal to the mass of carbon plus 2.66 times the mass of carbon. And the reason I'm doing that is because the mass of oxygen is 2.66 times the mass of the carbon. So the mass of oxygen here would just be 2.66 times the mass of carbon. Now note that we have mass of carbon plus 2.66 times the mass of carbon. Well, that would just be 3.66 times the mass of carbon. And that would be equal to 105 grams. So the total mass, 105, is now equal to 3.66 times the mass of carbon. Well, let's divide both sides by 3.66. And that gives us the mass of carbon. That's a simple calculation. So 105 divided by 3.66 gives us around 28.7. So 28.7 grams equals the mass of carbon. Now the total mass is 105 grams, so if we know the mass of carbon, we can find the mass of the oxygen, the mass of oxygen would just be 105 grams, the total, minus the mass of carbon. So the mass of oxygen would be equal to the total mass, 105, minus the mass of carbon. So that would be 105 grams minus our 28.7 grams. Simply put, 105 minus 28.7, that would give us 76.3 grams. And again, that's the mass of the oxygen. So now mass of oxygen, 76.3, and the mass of the carbon, 28.7. You could do a check and see that if this ratio is equal to 2.66 to 1, and it would be. And so there's our calculation. Okay. Now, we want to talk just for a moment about something called the law of multiple proportions, which sounds a lot like the law of definite proportions, but this is a slightly different view or a slightly different interpretation. This says, this is from your textbook, if two elements can form more than one compound with each other, the masses of one element that combined with a fixed mass of the other element are in ratios of small whole numbers. That's from Burge on page 41. So let me show you some data here. This is the data we just looked at. Carbon dioxide, that is a compound of carbon and oxygen. The ratio was 2.66 to 1 for the mass of oxygen to the mass of carbon in each case. Now here's another compound. This is called carbon monoxide. Carbon monoxide is a different compound with different properties than carbon dioxide. And we can do the same sort of experiment to determine the mass of oxygen, the mass of carbon in carbon monoxide as we did in carbon dioxide. But here what we would find is that the ratio is not 2.66 to 1 oxygen to carbon, but 1.33 to 1 in each case. So that means there's less oxygen per carbon in carbon monoxide than there is in carbon dioxide. So what we do is we take the ratio of oxygen to carbon in one of the compounds, so let's say CO2, carbon dioxide, and that was 2.66. Divide that by the ratio of oxygen to carbon in carbon monoxide, which was 1.33, and that ratio should work out to a small whole number, like 2 or 3 or maybe 4. In this case, it works out to 2. That tells us that there's twice as much oxygen in carbon dioxide relative to carbon than there is in carbon monoxide. Okay? Now note, if we'd done it the other way around, if we'd put the carbon monoxide in the numerator and dioxide in the denominator, we would get 1.33 over 2.66, which would be a half. So it's still a 1 to 2 ratio as opposed to a 2 to 1 ratio. Small whole numbers. Again, this is evidence for the only way this would work out is if you keep doing this experiment over and over and you keep getting these whole numbers like 2 to 1 or 3 to 1, that means that we really, the only way to explain that is that there are definite numbers of particles, and we would call those atoms. If matter was just more ethereal, meaning you could just keep dividing it into smaller and smaller pieces infinitely, then you would have essentially an infinite number of compounds for carbon and oxygen. You could have maybe not 2 to 1, but maybe 2.1 to 1 or 2.12 to 1. You can just have all sorts of different compounds. But what we find in nature is there's a limited number of compounds, and that suggests that we have atoms. The third relationship talked about in this section is what's called the law of conservation of mass. You've probably heard of this before, and this says that in a chemical reaction, the total mass of reactants and products does not change. So if you have a chemical reaction taking place, there's not going to be a change in mass. So let's come back to that original reaction we looked at before. This is actually the combustion of methane, CH4, in oxygen. So oxygen reacts or combusts with methane. We'll talk about this more in chapter 3 to form carbon dioxide and water. If we did a very precise measurement of measuring the amount of methane, CH4, that we put into a reaction vessel and the mass of the oxygen that we put in, let's say we put 16 grams of methane in and 64 grams of oxygen, the total mass here would be 80 grams. Now you might argue, based on our previous discussions in Chapter 1, that that's not a very precise measurement. We're only measuring it out to the gram. We're not going even to 1/10 of a gram, and that would be a valid criticism. But let's just start it off that way. 80 grams of methane and oxygen reacted. Now I've picked numbers here that are matched so that all of the methane and all of the oxygen will react to form carbon dioxide and water. And note, if we measured the mass after the reaction was done, we would also get 80 grams. So this is after the reaction, and this is before the reaction. And note, the reactants, the mass of the reaction, I should say, is equal to the mass of the products, 80 grams. So you say, okay, well, maybe it's just worked out that it's 80 in each case, but what if I was more precise? Okay, we can do that. Let's now try 16.05 grams of methane and combine that with 64.00 grams of oxygen. So now we're going out 2 sig figs past the decimal point, and the mass will be slightly different, 80.05 grams. And we measure the mass after the reaction is complete, and what we would find is, yes, going out 2 sig figs past the decimal point, we still get the same result, meaning that the mass after the reaction is the same as the mass before the reaction. This is the law of conservation mass. We could go out even more sig figs, 3, 4, 5 sig figs, and we would get the same result. Now, your textbook has a little footnote talking about Einstein's work, which suggests that mass and energy are really related to each other, so that when a chemical reaction occurs, some of the mass can be lost as energy. We won't worry about that in this course, but that is something that if you want to research it further, you'll find that that is the case. For chemical reactions, generally, the mass before the reaction is equal to the mass after, as long as we measure the masses of all of the materials in the reaction. So at this point, what you should do is you should try the practice problem from section 2.1.